Good morning. I hope I'm audible, right?
Yes, sir.
Okay, so we'll get started. Is the slide visible?
Yes, sir.
Okay. So we have been discussing about inheritance, the most important principle of object-oriented programming. The fact that in real world, many of the concepts that we need to deal with, many of the concepts that we need to program into, are interrelated between themselves in terms of is a relationship. One is a specialization of other or generalization of other. And in terms of that, we have seen how to write base and derived classes on this hierarchy in terms of public inheritance. And we have seen the principles of how to construct and destruct such objects of specialization. And we have seen that any specialized object contains an instance of its generalized object or the base class as a part of it. But depending on the access specifier, it will be allowed to access only the public part of the base class. Then we have introduced another form of specifier called the protected specifier, wherein a derived class can access the protected members of the base class, whereas anyone else outside of this class hierarchy or say a global function cannot access the protected members that behaves like a private member only. So that is the fine tuning that we can do in terms of this. And based on that, I had requested you to go through this module 24, which presents the example phone hierarchy. So I'll quickly just go through that and then proceed. So this is just as a little bit more detailed example of phones that we had talked of, comprising landline, mobile, and smartphones. So these are the kind of we say are helper classes. Helper classes in the sense that these are not a part of the hierarchy, but these are uh, the classes corresponding to different data members, different attributes that the phones will need to deal with, like the class phone number, class name of the subscriber, class photo, which could have the image of the subscriber and the subscriber name as an alternate text, the class ringtone, the audio of the ringtone and the tone name, the class contact, which we will certainly need a collection of them, the phone number, name, photo, optional of a contact, class address book, the list of contacts, and so on. So these are the different helper classes we'll need. So with that, if we model a simple landline phone, which has a phone number, subscriber, and ringtone, and we have a few public methods, like obviously the constructor. You would need at the minimum the name, the number, and the name, and then a public method to set a call to a phone number, a method to answer a call, and obviously you need the output streaming operator to be able to print any instance of this landline phone class. When we go to mobile phone, we have a more detailed set of data members, phone number, subscriber. Along with that, we have ringtone, address book, the phone number last dialed, private members to set the last dialed number from the dialing call function, showing the number, and so on. And we have a set of public methods. We have overloading of the call function now, because we can call by phone number or we can call by the name. We have answer as before. We can redial, set a ringtone, etc. If we go to smartphone, we have a similar set of data attributes. Along with that, we will have a size of the smartphone, the display size, method to display photo, two versions of the call as before, setting the ringtone and so on. So this is the overall comparison that we had seen, where we can place them in a hierarchy. So we can say that a smartphone is a mobile phone, is a landline phone. So as you can see that each one of them have call, but the call mechanism should be different. So there is, you can clearly see a possibility of overriding and overloading here. Similarly for the answer, certain operations like redial does not exist in landline phone, we are showing, but it exists in mobile phone and smartphone. Similarly, add contact is not there for landline. So these are the different methods that you have. Here by notation, we will see this later on more. By notation, usually plus before a method name indicates that it's a public method. Otherwise, it's a private method. So this is the hierarchy. The hierarchy is transitive, as you know. So now we can code that in terms of putting the landline phone code and the mobile phone code side by side. So this is put in more detailed terms. This is how the ISA hierarchy will look like. So if we now put it in the hierarchy, then we have mobile phone, public, landline phone. Right? So this is what is the hierarchy will look like, and then we will have a call in the one second. The call in the mobile phone with the phone number is a overriding, because certainly it was there in the base class, but call with a name is a overloading. So you can clearly see that. Possibly answer may be skipped if we do not want a different functionality, because you will inherit it from the landline phone. Others are new functions. Similarly, from mobile phone now on slide 14, you can specialize smartphone, where you override call, both calls again. Mind you, in mobile phone, the second call by name was overload because it was not there in the landline, but in the smartphone, it is an override. Similarly, redial is an override and so on. So that is how the hierarchy goes. And you can even generalize it further, saying that, well, I do have a concept of a phone. What is phone? Phone is, as we said, is telephone, Durbhash, where you can call, answer, and redial. So I put an abstract concept of a phone and then specialize into the landline phone. I'm using some kind of a notation we have not introduced yet, because for an abstract phone, I will have a call mechanism, but I do not know exactly how to do that call. So I will not be able to have a body. So this is what this, is equal to 0 means. It means it's a pure virtual call. We will talk more about that, but it basically gives a very abstract model of phone. And then we say landline phone is that kind of a phone. Mobile phone is a kind of a landline phone. Smartphone is a kind of a mobile phone, and so on. So that's how the hierarchy keeps building up. Here I have, just, for the sake of, looking into how real life hierarchies can grow, I just put one here. So on top of this, you could have the phone, the general concept, but a landline phone could be a speaker phone or a cordless phone. A mobile phone is a speaker phone as well as a cordless phone. It does not have cord. So you see here a kind of inheritance that you have not seen before, where one class is specialization of two. We have seen single inheritance, we have seen multi-level inheritance, we have seen hybrid inheritance. But for example, there's a single inheritance, there's a hybrid inheritance. This whole thing is a multi-level inheritance, but this is something which is special, which is called multiple inheritance. That is one class being specialized from two. We will also look at more instances of this in future. Then a smartphone is a mobile phone. Then we have different types of smartphones: tablet phone, Android phone, iPhone, and so on. But a tablet phone is also a video phone, and a video phone is also a landline phone, and so on. So you can imagine the reality and keep on having hierarchies as you go ahead. So this is just to give you a full feel of how a real hierarchy could do work. You could pick up your domain and start building the hierarchy. There's kind of an endless game. Okay, we will get into the next where we talk about inheritance that we have seen so far is only public inheritance, and we'll see inheritance can be different also. For example, again, recap: derived is a base. This is the diagram. This is how we write. Base class is base, derived class is derived. We use the public keyword after the class name to denote inheritance. This is the core sense of inheritance. This is the sense of inheritance in object-oriented terms. So this is what we have seen. There's a base class. There's another base class. Or that there's another class. There's a derived class, which is inherited from the base class. So this is what we have seen. That's inherited base class. Inherited derived class has a C class data member. So this is a general scenario. You can see what the output would be. This is in terms of constructor destructor. Okay. Now, the interesting point is, like we have three different access specifiers, the inheritance logic in C++ also has three flavors: public, private, and protected. So which means that I can write class derived colon private base instead of writing public base. I can write private base. The word of caution and very, very strong word of caution for you to remember is, if you use private or protected, if you are not using public inheritance, then it is not a generalization, specialization, hierarchy in the object-oriented sense, not at all. Private inheritance means, it is called inheritance, but it means something very, very different. Private inheritance means nothing during software design, but only during software implementation. Often some of the authors like Scott Meyer call private inheritance as is implemented in terms of kind of semantics. Let's see what it means. So on left is a public inheritance. I have a person. Student is a person. So student colon public person. Anyone can eat, takes a person. Only students can study, takes a student, right? Well, so I have a person instance P, I have a student instance S. I can eat, the person can eat, P can eat, so it's fine. The student is a person, so student can also eat. So eat S here. Student is a person, is a specialization. Student is a person, so student can also eat. Study S is fine, student can study. Study P is an error because P is not a student. Right? So you can see that if you have a more generalized class as a parameter, it is possible to pass a specialized class instance into that. This is possible because when I pass eat S is an instance of student which has a part which is the instance of person, the base class instance of S, right? So when I call eat on S, the base class person part of S gets passed as P, and it can fully function. But when I do the reverse, the study needs the whole of the student class. That is the base class part of the person as well as the student additional part of the student class. So if I pass P onto that, which is just the person, which will mean the base class part of the student, The other part is not known, so that cannot be allowed, right? So you can always pass a more specialized object to a generalized interface, but not the other way around. Okay, so that was by the point. But our core point here is public inheritance. Now suppose I make this change. I change this to private inheritance. I call it private. Nothing else changed in here. Just this word private changed. P is a person. It P is fine, right? The person. It S is an error. That is no more allowed because private inheritance is not a hierarchy. It does not mean that student is a person. So more importantly, what it means is that anything that I had in a person has become private in student, and student is no more to be treated as a person. Rather, student may be thought of having been implemented using the base class person. Right? So this is a basic difference you will see. If you change this to private, it S will stop compiling. Study S will be fine, and study P will obviously not compile for the earlier reason itself. Similarly, there is another called protected inheritance, where you can use the keyword protected. I cannot give you a meaningful example of protected inheritance. I can only say that it also does not mean generalization, specialization. Because I mean, possibly having protected inheritance was kind of a I should say an inertia of definition that the language designer used, but there is no well understood semantics for the protected inheritance. So this is what Scott Meyer says. Private inheritance means something entirely different from public inheritance, as we have mentioned. Protected inheritance is something whose meaning eludes me to this day. I mean, so does me. So protected inheritance, the basic rule is don't use. Let it be there in the language. It is there, but it's not been used. Now the question is, what happens to the access specifiers or the visibility when you do this inheritance? So far we have seen only public inheritance. So if you do public inheritance, then anything that was public in the base class is public for the derived class. Anything that was protected in the base class is protected in the derived class. Anything that was private in the base class is obviously private in the derived class. But if you do private, everything becomes private. So anything that was public in the base class becomes private in the derived class. Anything protected becomes private. Private, of course, remains private. We would not be doing this, but if we do protected inheritance, that anything that is public becomes protected, anything protected is protected, private is private. So, I mean, kind of this is the diagram that shows that this is what you have in the base and this is what happens in the. So you can see access base. Basically what it's doing, it is getting more conservative. Protected is more conservative than public. So when you use protected, anything which is more open compared to protected becomes protected, like public becomes protected, but others remain same. Similarly, when you use private, anything which is more open compared to private, that is protected or public, they become private. So this is so primarily this and this, the first and the last. The first is public where nothing changes, and the last is private where everything becomes private, is the basic rule to remember. So this is the private inheritance, and this is what you will have as output. You can see you're constructing D, constructing an instance of this class. So it derives from C, which derives from B. So you need to construct B. Then C naturally will get constructed from this. Then you have a data member C. So again, we'll have another call to B. We'll have another construction of C, the data members done, and then you'll have the actual construction of D. So in terms of constructor calls and all, nothing changes, but certainly in terms of visibility of and usage, things would become different. Right? So you can see the inaccessibility of members as of here. So A has private protected public, B has private protected public inheritance, C has protected inheritance, D has private inheritance, and these are the public bases. So you can see that when you look at the different accessible members, the accessibility keeps on decreasing. The specific examples given here, just go through that, should be easy and straightforward to do. Now the question is, well, should we use private inheritance? Now, there is another concept in object-oriented design systems that I would like to bring in here, which is called HAS-A. HAS-A is a composition. So IS-A is specialization, HAS-A is composition, that if I have a an object that is composed of a number of sub-objects. Every sub-object will be composed of number of sub-objects and so on. Right? For example, a car is composed of engine, steering, body, chassis, brake system, and so on. So those are compositions. So let's say if we write like this, I have class engine. Look at the left side, which is composition. So I say engine. Engine has some number of cylinders and all, and then it has a function. Engine has to be started at least, so there's one function start. I have a car which has engine as a data member. So this is when you have a data member, you are actually expressing a composition. So you're saying car has an engine. That is E underscore. We make it E8 here in the constructor of car, which says that I'm initializing a car with an 8-cylinder engine. Okay. Then I provide a start method in car. So this is a separate method altogether, because car is a separate class altogether. It's nothing to do with the start here. So all that it says that starting a car is same as starting the engine. There may be more things, but that's a simple thing. Then you construct a car C, which as a part of the composition will construct the engine E, and then you do C dot start, you start the car, which in turn starts the engine. So that's a behavior you have modeled in this simple composition. Okay. Let's look at this in terms of private inheritance. So what you are trying to say in this is, forget about the general sense of inheritance. What you are saying is car has this private part called engine. Private inheritance means that having that as a private part of yourself, implementing it as in terms of that component. So I have the same engine, but car I change. I make car private engine. Mind you, if I made public engine, it will mean completely different. It will mean that car is an engine, which is not true at all. But when you say private engine, what I'm meaning is car has an engine. That is, car internally encapsulates an engine. So then car is engine 8, because since this is a case of C++ inheritance, any car object will have the instance of an engine object, because it is on the inheritance in C++ hierarchy. So it needs the construction of the engine object here. So I construct engine 8, similar to the construction of 8-cylinder engine here. And then I'll say that start this car by starting its engine. So I say that by doing using. Why? Why I have to do that? Why can't I just let c dot start be used here? So this part is tricky in terms of the rules. Just think carefully. This is the base class engine. I'm talking purely C++ now, not general object oriented sense, but this is a base class. This is the derived class, privately derived, right? In this base class engine, start is a public method. So car can inherit it, car can use it. But in car, since I've used a private inheritance, I'll become conservative. So what happens? I'm going back from 14 back to slide 10. What happens when I do private inheritance? Everything becomes private. Every member I have inherited becomes private. Getting back to 14. So after private inheritance, car methods can use start, but anybody external to the car will not be able to use the start method of car, because in car, the start method has become private because you are privately inherited. Right? So you have to explicitly make it available. To make it available, you say in the public, you're saying using engine : start. So when you say that, it means that in the public, you are making engine : start method, which car has inherited as private. You are making it available in the public. So this is, we have seen using in the in the context of namespace. Here is another use of using, where you are actually changing the visibility of a member, saying that using engine : start, which means that the start method of engine that car inherited as private can be used in the public. So only then you will be able to do a c dot start from main, because it is external to car. If you do not have this c dot start becomes a compilation error. So you can see that this is the conceptualization of private inheritance in C++ vis-a-vis composition. There has been severe debates in terms of whether you should be using private inheritance, but the general consensus is that whenever it is possible, you should use public inheritance. You should use composition, not use private inheritance to mean composition. It is simpler and it is more explicit. The semantics is clearer. The syntax is cleaner. It is easy to read. Use private inheritance when you really need some implementation property to be propagated along the hierarchy. For example, if you want to make a hierarchy where you do not want things to be copied, so you can have a base class which is uncopyable. How do you make some class uncopyable? Very simple. To copy, you need to have a copy constructor, right? Only then you can copy. Now, if you make that copy constructor private, then you will never be able to copy instances of that class. So if you create such an uncopyable base class and inherit your whole hierarchy from that base class, that will mean that on the entire hierarchy, none of the classes will be able to have objects which can be copied. So it's a non-copyable hierarchy, which means that no object of that hierarchy could be used as call by value, because that needs a copy, right? So there could be certain semantic consequences which you can express in this way, and it is not possible to have this semantic restriction in the program by doing composition, because this is not composition what you are mentioning here. Here you are trying to say that I want to inherit an implementation property on the hierarchy, not a design property. Specialization generalization is a design property. It is a property of the real world. Implementation property, right? Whether I want to copy a objects of a class or I don't, is an issue of implementation. So when I want to have these kind of implementation principles propagated along my otherwise normal hierarchy, otherwise normal, generalization, specialization hierarchy, I could use a base class which has this restrictive property and inherit the root of my entire hierarchy privately from that base class and have that whole property propagated all through, right? So may sound a little abstract, but I would like to I like you to think it over and see how it really implements. Okay, so that brings us to the end of general discussions on inheritance before we go into the actual, the core consequent principle of inheritance, that is dynamic polymorphism, which is a core part. Before that, let me ask if you have any question. No questions?
Sir, am I audible?
Yes, please, Shunanda. Shunanda, is it?
Yashika.
Yashika, please.
Sir, in slide number 12, if I inherit a private class, like it is defined public, but I inherit as a private C, right? Like you mentioned just now. So will the original base class of this class be accessible to me, like in slide number 12?
This slide you are saying, right?
Yes, sir.
Slide 12 you mentioned.
Yes.
Okay. So now you say in terms of the name of the class?
Yeah, in class D, we are doing a private C, right?
Right.
So private C has is a subclass of public B.
Right.
So when I define D as private C, will the class B be accessible to me?
Yes, because see, the question is where. Start from the root. Class B has these constructor destructor as protected, right? So that means nobody can construct an instance of class B from outside, right? Is that clear?
Yes.
Right? Because these are protected.
Yes.
Now class C is public B. So it inherits everything of B. In public, the access specified does not change. So class C gets the constructor destructor of B as protected, and they remain protected in class C. Similarly, class C have its own constructor destructor as protected, right? So which means nobody can construct an instance of class C either, right? You'll not be able to construct an instance of class C, right? Now you come to class D, where you are inheriting from C through private, which means D gets everything as it has got in C. But in D, they become private. So D can access the constructor C and the constructor B if it needs to, because it has inherited them as protected. But in D, they have become private. So if I further inherit something from D, then they will not be able to use C directly, the constructor of C directly. So the way we are doing is we have instantiated a D in main. So that needs a public constructor of D, which I can access. Public constructor of D needs to access the protected constructor of C, which I can access because it is protected in C and D is inherited from C. But if I had inherited E from D, then E will not be able to use the constructor of C directly, because in D that has become private. Got it?
Okay.
So at every stage, you'll have to go at every stage. What you inherit is what you can use. So because the inheritance is private does not mean these constructor destructor which are protected in C becomes, I mean, D has inherited them. They were protected at that time. So it is with respect to C what D can do. D is allowed to use them. But in D, they place them as private. So others who come to D will see that as private. Getting me?
Yes.
And I would suggest just try out a couple of examples. Try running them. It's good fun. You'll be able to really, these are small code. Just run, make the changes, try to access it. It will immediately become clear as to what it is doing. Okay. Chalo, let's proceed. So now we will go into the second part of the core concept of object-oriented design, which is built on top of the inheritance hierarchy. So far we have seen that I can inherit. I can create a hierarchy. Over that hierarchy, I can share properties of the base class in the derived class. I can redefine a property. I can add a property. I cannot disown, but I can reuse heavily. Right? So inheritance has given us the ability to override along with overloading. Slides are not visible. I'll try to do it again, but you have these slides, right?
Yes.
So this is in terms of the PDF file, this is slide number 445. But I will just disconnect and connect again to see if things. Can you see it now?
Yes, sir.
Yes, sir.
Okay. I don't know what goes on in the system. Anyway, so the second part, which is again very important part of the inheritance hierarchy is, so we have seen the sharing of properties. Now we'll see what is known as polymorphism or virtualization or dynamic binding, different names from different perspectives. What does it mean and how does that really make programming in C++ a very powerful mechanism? So we'll slowly develop into that. We'll first look at what is simply known as casting in a class hierarchy. Then look into static and dynamic binding, and then slowly go into the polymorphism. Okay, so having done PDF, you know that casting is a situation where the value or variable of one type is used in place of another, right? So, if it is, so this is a C example. If int is initialized with 3 and double is initialized with 2.5, then I can say double result is initialized with d by I. So this is called a mixed mode operation, I being an int and d being a double. The division is not by default defined. So what the C compiler does, it casts I to double, changes its format to double, and then uses a double divider and use it. Now, this is an implicit casting. Going forward, you can see that the casting could be implicit or explicit. For example, again, I is int, D is double, and P is a pointer to double, which is initialized with the D object. So if I do I assign D, it is implicit and it is allowed because I'm taking a smaller object to a larger class. double is larger, int is smaller. So this is implicit as well as permitted. If I do the reverse, I assign D, this is implicit, but you get a warning because you are taking a larger object and putting it into a smaller object. So this is there is possible loss of data. So you get a compiler warning. There is compiler switch also to stop this implicit conversion to happen. But you can still get it without a warning if you do an explicit casting. You say in front of D you can write int, where you are saying telling the compiler in a way, look, I'm grown up, I'm adult enough, I know what I'm doing, so don't give me a warning. I'm taking D and converting it to int and using it. Right? This is an explicit casting where you are explicitly telling the compiler that what to take and cast to what. You take I, P, cast it to I. P is a pointer, you are casting it to I, which is an integer. Obviously, this is an error because you cannot convert a double star pointer to an int. Even though the systems maintain that the size of a pointer and the size of an int are the same, but they mean completely different things. But if you are explicit, you can do that. You can explicitly cast a pointer to an int by doing this. Right? So this is the implicit and explicit casting. We will come back to the hierarchy. We need this recap to really cast ourselves well. So now we have two classes. We have wrapped these two into two classes, class A and class B, and we create instances of A and B. We create two pointers also, one of A, another of B, having the corresponding objects. If I assign B to A, I will have an error because these classes, the right hand class takes is main : B, and left hand classes main : A. They are unrelated classes. There cannot be an assignment. There is no operator which can do this assignment. So this is an error. I can try to do a cast. How do I do a cast? I take the B object, and like in the same syntax I was doing int, I put class A. It will say a typecast error, cannot convert B to A, because what does this mean? This means that for putting it to A, I need an A object, which means I need the constructor of A to be invoked in a way. Invoked with what? A B object. Now the class A does not have a constructor which takes a B object. So the conversion is not possible. It gives you an error. If I do the reverse, B assigned A, I get similarly an error. If I try to typecast B A onto B, I get the same error, because now it does not matter what is the inside data member types are. It matters that they are disjoint class. So if I have two unrelated classes, casting is not possible. Right? If I try to do Q to P, which are pointers, both are pointers, same size, but it's not possible because they point to objects of two unrelated classes. Similarly, the reverse assignment is also not possible. But using pointer, you can do a forced casting. You can take the pointer to B, address of B, and cast it to a pointer of A, and vice versa. These are allowed. In terms of pointer, explicit casting of unrelated pointer types are allowed. Right? Now, why it was allowed is a different question. At some point of time, you'll realize that. But for now, just take that. If I have two unrelated classes, there cannot be any casting of those values, except that I can explicitly cast pointer of one type to the pointer of other. Right? So this is your basic casting rule so far as classes are concerned. Now, forced casting between unrelated classes is dangerous. So I have the same two classes. I've just made them public to be able to assign values to them. So I have the object instances A and B. I have pointer instances to A and B. I can do P pointer I, Q pointer D. works correctly. Suppose I do a casting of the pointer. I take the address of B and cast it to as a pointer of A. So now P is a pointer to A, so I can do P pointer I. But P pointer I is actually pointing to a value which is 7.2 in double. So it is taking some part of it and trying to think it is an integer or something. So on my system on that day, it printed this, which is a garbage. I do the reverse. I'm taking a pointer to B, but my actual object is A. There's an integer 5. And I'm trying to take that 5 and some more bytes beyond that and treating that as an integer, treating that as a double, and I get on that day on my system, I got this. That's a garbage too. So, casting force casting between unrelated classes, direct casting is not allowed by the compiler. Casting through pointer is allowed, but it is dangerous. So keep all of that outside of what we can and should be doing. But casting on a hierarchy is permitted in a limited sense. Let us see what. So this is when now the casting and inheritance come together. So I have class A, I have class B, which is a specialization of A. I have pointed to A, pointed to B, both initialized to 0. I have a void pointer, also initialized to null. Now I can assign PB to PA. Why? Because PB is supposed to be a pointer to the B class object, which has as its part an A class instance. Okay? So if I assign PB to PA, that is a pointer to an A class object, what I get to use is the A class part of the B class object to which PB was originally pointing. So it's valid because there is an A class object inside the object being pointed to by PB. Right? So this is okay. This is known as upcast. That is, you have an instance of a more specialized class and you are treating it as a generalized class. So you are making less assumption about the object than actually what exists. So you are going up in the hierarchy. So it's called upcast. Try to do the reverse. Try to assign PA to PB. This is a compilation error. Cannot convert A star to B star. Why? For the simple reason that you have an instance of class A and you are going to treat by this pointer assignment, PB will point to a B class object which needs a base class instance plus whatever is additional for the derived class B object. That is not there because PA was pointing to a class object only. So it does not have the additionals of class B. So PB will have some garbage in the assumption of the class B members which are not inherited from A. So this cannot be allowed. This is an error in the compilation. However, either of them can be assigned to the void star. Because in void star, you are saying, I know nothing. You knew a lot in PA. You knew that it points to a class object and you can find a class object, these many data members, all that. But you are just choosing to forget. You are just saying that, well, PA is a pointer. What does this assignment mean? This assignment means that you are telling that I know PA is a pointer. That's it. So that value is PV, which is void star, which says there is a pointer, which is a pointer. So it is, both of these are okay, but you certainly lose that type. But if you try to do the reverse, this will not be allowed because PV is a pointer to, you don't know what. So what if you assign it to PA? You are expecting a class object and you don't know what you have here with PV. Similarly with this. So this is what is not allowed. What is most important is the first two rule that upcast is okay in a hierarchy. Downcast is not. Downcast is information losing. Upcast is information preserving. So we say upcasting is safe. Let's look more. I have class A, int A, class B, int B, specialization of A and B instances. So class A object will have only data A. I put it here. Class B object will have data A and data B. I have put it there. I've created pointers to both. Using PA validly, I print the class A object, prints 2. Using PB, I print the class B object, prints 3, 5. Then I take the class B object's address and put it to class A. What will mean that the class A part of B, class B object, will be accessible. So now if I do PA pointer data A, it prints 3 because B dot data is 3 and PA is actually point to the B object. It prints 3. But if I do PA pointer data B, I'll get a compilation error because PA knows that it is a pointer to A and that does not have a data B member. So that part will not. So it is safe, and the compiler rightly restricts me from accessing data B, which in this case exists, but in general may not. But it seamlessly allows me to use the base class part of the derived class object. So this is upcasting. I'm going from B to A up in the hierarchy, and I'm allowed to do that. Okay. So in this context, the static and dynamic binding will be introduced. Right. So look at this class B and class T, a simple one single inheritance case. There are 2 functions in B, 2 functions in D. Neither of the functions take any parameter, nor they return anything. Between F and G, the difference is that B has put a word virtual before this function G. Function B has overridden both these functions individually. And all that functions do is just say that they are being called. Right? Now there are 2 instances created. Now initially PB has the address of the B object. PD is also a pointer to B. So its type is pointed to B, has the address of the D object. Right. Let us just take up to this much. Later on we'll see. The reference part we'll see. Keep that on hold. Now if you do B.F, B.G, they will call the B, obviously the B functions. If you call D.F, D.G, they will call the D functions. This is simple, simple function method invocation from objects. There is no surprise here. Now let's say I do PB pointer F. PB is a B type pointer pointing to a B object. It calls B colon colon F. PB pointer G calls B colon colon G. I do PD pointer F. PD is a B object. PD is a pointer to a B object, but currently contains a D object. So PD pointer F calls B colon colon F, but PD pointer G calls D colon colon G. You can see the difference. You see the difference. By making this virtual, you have made the binding dynamic. What does that mean? When it is not virtual, it is the type of the pointer that decides which function you will call. The type of the pointer is B star. It's a B class pointer, so you'll always call B class function. So PB pointer F calls B class F, PD pointer F calls B class F. But when you make it virtual, it becomes a dynamic binding. It means 2 things now. One is this pointer to this base class must have this function available in the base class. That's the first requirement. If G were not there, then this code will not work. But having got G, it will not necessarily call G because it is pointed to the B class object, B class. It will call G if the object it is actually pointing to is a B class object, as in here, PB. It will call the function of the B class. But if object that it is pointing to is actually a D class object, then it will call the overridden G function of the D class. So it changes. Signature wise, they look the same. I mean, if you look at the call signature, they look the same. But the behavior changes in terms of which function it calls, depending on whether a function is non-virtual, a method is non-virtual, or it is virtual. The rest of the example is similar, but it's done in terms of reference. So if you do it in terms of reference, if RB is a reference, B-type reference to object B, and RD is a B-type reference to object D, then you see the same static and dynamic behavior using calling these functions through the reference. So the conclusion is if you have virtual functions, they engage in dynamic binding. If you call the function directly on the object, it still calls the statically bound function of the respective class. But if you call it through pointer or through reference, then it will have a static binding for non-virtual functions and a dynamic binding for the virtual function. And that creates a whole lot of consequences in the whole thing. Right. So I will stop here. 2 minutes left. If there are quick questions, I'll take. Otherwise, I'll continue on this further in the class tomorrow. Any question? We have introduced two very crucial notions today, besides those private and protected inheritance discussion. One is of casting, and particularly looking that casting on a hierarchy could be dangerous. It is safe if we upcast, and it could be dangerous if we downcast. And we have looked at that based on a hierarchy, we could have dynamic binding of functions. That is, signature wise, it might look that we are as if invoking a method in the base class, but in reality, it invokes a method of the derived class. How that happens, consequences in terms of what great benefit it brings us, we will have to discuss, show examples. Any questions, friends? No? Okay, we are exactly out of time. So let us stop here today. See you at 12 tomorrow. Have a good day, and we'll continue on this.